Thank you. Thank you for including me in this meeting. It's great to be here. So the tutorial is going to be on Hugh's theory of AD+. The intention is to cover sort of the classical, pre-classical theory, which comes roughly from the seminar from 1994-95. The parts that don't use any of the stationary tower or inner model theory, so the classical combinatorics, I'm writing a book on this, so most of what I'm doing is in the book. The book may take me forever to write. I don't know if I'm actually going to ever finish the book, but to make up for that, I'm posting drafts of the book online as I process things. So you can find the book online if you Google one of the following things, right? So if you Google Larson extensions of the axiom of determinacy, that pulls it up, at least when I do it. The axiom of determinacy. Somehow I internalized the idea that you shouldn't use symbols in your titles, and so when I put AD+ into my desymbolizer, that's what came out. Extensions of the axiom of determinacy, so that's the title of the book. The actual file is called AD+ book _public.pdf. So I think if you Google that, you get it also. If you cut the public off, you shouldn't find anything, but I don't know, who knows, we'll see. All right, so that's the plan. What should I say? Nothing in the talks is due to me. Eventually, it's all due to Hugh. There's a lot of background to get to first. Talk 1, which I've prepared, I mean, it's 7 typed sheets of paper. I have no idea how long anything takes to do. It's possible that I will blow through it in 20 minutes, or it's possible that it'll take 3 hours to do. We'll find out. I'll tell you in a second. I'm not committed to using all 6 hours that I have. I may stop early. There was suggestion that I should take a break at some point. I'm happy to take a break at any point that anybody feels like taking a break. That's fine. 2, I mean, this is a 90-minute block, but we can stop at 45 minutes if anybody feels like it. Okay, so we're just going to start. But lecture 1, which may take 2 lectures, we'll see, is supposed to be very gentle. The idea is to keep everybody on the bus for the first 7 pages of notes. We'll see. So for some of you, it's going to be very basic. I mean, at the very beginning, I think it's going to be very basic for everybody. But the intention is to make it accessible to everybody. Please ask me if you have any questions about anything, if you want me to go slower or explain more, or please ask any questions that you have as we go. Okay, so here is the plan. I'm probably not going to do it in 20 minutes, as we'll see. So, I mean, lecture 1 it's all definitions, questions, statements of theorems, and very soft proofs. No complicated proofs at all in lecture 1. Okay, so we have lots of terms to introduce. I guess the target is to prove some of the theorems that were in the background of Steve's talk. So Steve had some background AD+ theorems in his talk, and the goal of really all 4 lectures is to sketch proofs of those things eventually, but not to sketch them today. All right. So here's the menu for today. The things I'm going to introduce fall into 2 categories. We have sort of statements, or maybe we call them axioms, I don't know. So we have the following axioms that we're going to introduce. So AD and ADR come first. Uniformization is next. DC and DCR. Gama Determinacy. And finally, AD+. At the end of that list, we will define AD+, once we've gotten through that. While we do that, we're going to introduce some objects. I mean, the whole talk is about models of determinacy. There's various objects that help us classify or stratify or understand models of determinacy. So we have the following objects. We have the wage hierarchy, and the cardinal theta, Suslin sets, and infinity Borel sets. What else? Suslin cardinals, and the Solovay sequence. Okay, so we'll do as much of this as we can in the time we've got. I realize my handwriting is completely terrible, so if you can't read anything, which is likely, you should just tell me and I'll say it out loud at least or something. Okay. All right. So I think that's the pre-introduction. Very good. So first, AD and ADR, right, which probably everybody knows, but just we all start in the same place. Okay, so I'm going to introduce this notation that I'm only going to use 3 times, but let's just do it. So X is a set, and A is a subset of the omega sequences from X. We have a game, right? The game GXA between players 1 and 2. By the way, when I started writing this up, the game metaphor is helpful. I tried writing up all the combinatorics directly without the game metaphor. It's horrific. You get to the end of one page and you say it's impossible to write about any of this stuff without using the metaphor of games. It's impossible. Okay, so it's a game. Player 1 and player 2 pick elements of X. They pick, 1 picks F0, and then 2 picks F1, and 1 picks F2, etc. And in the end, they've built an F that's an omega sequence from X, and 1 wins if and only if F is in A, right? That's the game GXA. Okay. And we say the game is determined if one player or the other has a strategy that guarantees a win. Okay, so GXA is determined if one player or the other has a strategy. And okay, just to be concrete, what is a strategy, right? A strategy is a function that goes from finite sequences from X into X, guaranteeing a win. Right, so then no matter how the other player plays, as long as the winning player plays by the strategy, they win the game. Okay, so some observations about this situation. Okay, well let's observe. First of all, ADR implies AD, right? Oh, sorry. So I didn't define those things, did I? So AD is the statement that G omega A is determined for all A contained in the Baire space, omega to omega, like this, right? And then ADR is the corresponding version where we have G, it's the Baire space A, like that. So for all A contained in the Baire space to the omega. I only very grudgingly use this symbol here, right? I mean, of course we don't use the real reals everywhere, but, right? When tradition insists, I'll use this symbol here when it's harmless, right? But we always mean the Baire space by the reals. Okay. Okay, so that's AD and ADR, and so then ADR implies AD. That's the first thing we can observe. Right, the players are playing real numbers. Well, maybe the payoff set only depends on the first coordinate of each one of those real numbers. Right? You can code any integer game with a real game. AD, right, it's well known, implies a bunch of regularity properties for reals. So it implies what? It implies the perfect set property. Right, every uncountable set of reals contains a perfect set, right, which in turn implies that Aleph 1 does not inject into 2 the Aleph 0. There's no omega 1 sequence of distinct reals. Yeah? You with me? Is it okay or no? Oh, implies. Yeah. There's a very small arrow there. Yeah, right. It's not equal. Yeah, of course. Yeah. Okay. AD implies perfect set property, right? There's no omega 1 sequence of distinct reals as a result of that. It also implies all sets of reals have the property of Baire. That's in the background of some of these things we're going to talk about. It implies all sets are Lebesgue measurable. That is never used at all, as far as I can tell, in the whole theory of AD+. Never actually matters that all sets of reals are Lebesgue measurable, as far as I can tell. But it's also true. And these things are also consistent. Okay, so theorem due to Wooden. There are many theorems of this type, but we'll just go with this one for simplicity, right? If there exists infinitely many Wooden cardinals below some measurable cardinal, then L of R satisfies AD. There's a corresponding version of this theorem for ADR. There isn't really a nice model to tell you about first. I mean, in the end, after you have the theory, there's sort of a canonical model to talk about, but I can't really write the same. There's no pre-existing model I'm going to tell you about that satisfies ADR as a consequence of large cardinals, right? But this theorem, I believe, is due to some combination of Steele and Wooden, possibly independently. I don't really know exactly. No? It's not? Some combination of... Well, yeah, well, that's true. Yeah. Yeah, right. You don't know the theorem yet, but I'm going to do the analogous theorem for this. Is it just... Okay. Well, okay. I'll leave it blank. Well, I mean, is it your theorem? It's Hugh's theorem. Okay, sorry. Okay. Yeah, right. That's true. That's a totally fair point. But all right. So if same thing, but it's going to be instead of infinitely many Woodens. Okay. Yeah. Well, I mean, it is tough to assign credit in this whole thing. So, I mean, it's certainly the Martin-Steele theorem is fundamental in proving that theorem. That's true. Okay. So, all right. This one's going to say if there exists a cardinal kappa, which is a limit of Woodens and Strongs to kappa, and really this is not the subject of the talk, so I'm not really going to define these large cardinals because we're not going to use them. To kappa, all right, and there exists a measurable lambda above kappa, then there exists a gamma contained. Oh, I'll finish it, and then we can. There exists a gamma contained in the power set of the Baire space such that L of gamma and R satisfies ADR. All right. I think this is so okay. This is Hugh? Okay. Very good. All right, so I have it right there. Okay. All right, so these two axioms, I mean, for the moment, they're consistent. That's what we want to know. Now, one difference between these two things is what the strategies look like, right? In this thing, the strategies are coded by individual real numbers, and in this thing, the strategies are coded by sets of real numbers. Okay? So, okay, so AD implies that L of R satisfies AD, because L of R has all the strategies that witness AD. Yeah, thank you. Yeah. AD implies that L of R satisfies AD. Now, the same reflection for ADR implies that L of P of R satisfies ADR, okay? But it doesn't go down to smaller models, right? So it does not imply that L of R, for instance, satisfies ADR, or even models that look like L of A and R for A contained in the reals satisfy L of R, ADR, because these things are actually just false. Those things can't hold. Models of this form can't satisfy ADR. Okay, so in fact, these just never hold. And never true. Okay. So the first thing to talk about is the obstruction that prevents that from happening. I should say, I mean, there's a dream that I have, which is maybe not at all evident from anything that I'm saying. If you think of AD as giving you the right theory for the reals, maybe, and ADR telling you something about the power set of the reals, regularity properties. So this, if you'd like to extend this sequence, what does higher order regularity look like above the power set? I mean, John has some notes on this, which hopefully eventually I'll get back to someday. But these inner models of AD and ADR, they are very regular. They're sort of, there's a lot of canonical structure to them. You know, I mean, Steve talked about the natural models being the ones of the form L of P of R. Well, I don't know, what sort of natural structure can exist above P of R? Right? That's sort of something, I mean, it's not the topic of these talks at all, but something that's interesting to me. And in fact, I was telling Steve, I sort of object to the idea that these are the natural models. I mean, there are lots of natural models of determinacy that don't look like this, that have some structure above there. So, okay, but that's a separate topic. Okay. All right, so why does ADR fail in models like this? The reason is uniformization. Okay, so uniformization. Okay, so make sure this is all I need to say about it. So uniformization, which I'll just abbreviate as UNIF for this talk, is the statement that for all A contained in Baire space cross the Baire space, there exists a B contained in the Baire space cross the Baire space, such that for all X, right, if the set of Y such that XY is in A is non-empty, and again, that's just what we call AX, right? Then, right, the set of Y such that XY is, B is contained in A, first of all. In B has size 1. All right, so uniformization says, well, if I have a subset of the plane, right, there's a function such that for each non-empty cross-section picks 1 point inside, like that. Okay? That's uniformization. Okay. All right, so first of all, ADR implies uniformization, and it implies it trivially. All right, so ADR implies uniformization, right? If I have a set A like this, well, we have a game. In fact, the game only lasts 1 round, right? 1 plays X and 2 plays Y, and 2 wins if AX is the empty set or Y is in AX, right? And certainly 1 can't have a winning strategy in that game because he has to offer player 2 a non-empty set of options, and player 2 can always beat any strategy by picking one of those options, right? But then a strategy for player 2 is a uniformizing function, right? So you actually get something non-trivial out of this game that lasts 1 round. Right? Okay, so it's a very simple game. All right. However, models of this form can't satisfy uniformization. All right, so that's the next observation. So and this is due to Solove. Okay, so Solove. Right. Uniformization fails in models of the form L of A in R. Well, I mean, here we're thinking of A as a subset of the bare space, but the theorem's really more in general. In a model like this, every set is... Yeah, right. Yeah. Sorry. Assuming that omega 1 is not below. That's all you need. Right? If there's no omega 1 sequence of reals, uniformization fails in a model like this. In this model, everything is ordinal definable from A. Yeah, okay. I mean, I don't think it's the theorem I'm going to prove, but yeah, right, okay. All we care about is it fails in those models, right? Right, if this model satisfies determinacy, it satisfies this, right? So it's not going to satisfy uniformization. And the proof, I mean, the idea from the proof is pretty quick, right? We just let A be the set of, what, pairs x, y, such that y is not ordinal definable from A and X, right? If there's no omega 1 sequence of reals, then all the cross sections are non-empty. If there was a uniformizing function, it would be ordinal definable from A and some X, right? But then the corresponding value of your function would be ordinal definable from it, and that's a contradiction. Okay, so that makes sense? Seems all right? Okay. What's that? Oh, I have too many A's. Yeah, well, yeah, that's right. Let's call this something else, C, right? Now it matches my statement of, yeah, that's right. You're right, I overused A. Almost there. Okay? All right. Very good. All right. So very good. So that's one difference between AD and ADR. ADR implies uniformization, right? AD reflects down to models of this form, or reflects down to L of R, right? But uniformization can't hold in those models. That's one difference, and in some sense, we may see that may be the only difference between AD and ADR. Okay, very good. All right. That's all I'm going to say about uniformization for the moment. All right, DC and DCR. Okay, so DCX, where X is a set, any set, right, is the statement that for any tree on X, any tree, let's just say T contained in X to the less than omega, for any tree of finite sequences from X, if the tree doesn't have terminal nodes, has an infinite branch. Right, so this is certainly a consequence of the axiom of choice. If I have a tree and there are no terminal nodes, of course I can just go on picking nodes to the tree. Right? All right, so DC is the statement that for all X, DCX holds. All right, the notation doesn't hold the same pattern with AD and ADR, right? DC is stronger than DCR. Okay, so DCR is just DCX where X is R, right? All right, so DCR just says if I have a tree, the tree is just a set of finite sequences closed in their initial segments, and there are no terminal nodes. If the tree, if the nodes of the tree are reals, then I can find an infinite sequence through that tree. Let's observe uniformization implies DCR. Right? Right, if I have a tree on the reals, right? Finite sequences of reals, of course, are codable by reals, so then I can always pick a successor to any node. Uniformization lets me pick a successor from any node, and that gives me a branch through the tree, right? So uniformization implies DCR, so ADR implies DCR. Okay. All right. Should also add let's observe, right? DCR holds in models M when R is contained in M, which is contained in V, which satisfies the axiom of choice, right? Right, if I have an inner model that contains all the reals, right, it's going to satisfy DCR, because the witnesses, right, the paths to the trees are coded by individual reals. So if I have all the reals, I see any path that the outer model of choice does. Right, so our initial models that we sort of talked about for the consistency of AD and ADR, those are inner models of choice. Right, and so those are going to be models of DCR also. Okay? All right. Very good. Okay. I'm going to put this all together in a second, but the wage order. Okay, so given sets A, B contained in the Baire space, we're going to say that A is wage below B. Right? A is wage below B if there exists a continuous F going from the Baire space to itself, such that A is the preimage of B according to F, like this. So we can also say that A is, wage equivalent to B if the order holds both ways. All right, and we can define the corresponding equivalence classes to be the wage classes. Class of A. Okay, so that's an equivalence relation on sets of reals. All right. Now, Wage's theorem is that under AD, any two sets of reals are wage comparable in the following sense. Okay, so AD implies that for all AB contained in the reals, either A is wage below B, or B is wage below the complement of A. And again, it follows from a fairly simple game, right? We just have a game where players 1 and 2 each build their own reals. So one plays x0, y plays y0, x plays 1 plays x1, and so on. 1 builds x, and 2 builds y, and then 1 wins if and only if x is in B, if and only if y is in A, right? So a winning strategy for 1 is basically converting things from A into things in B, and a winning strategy for 2 is converting things from B into the complement of A. Okay? All right. Okay, so we get a linear, or almost linear hierarchy then on sets of reals. Now classes fall into two types. They can be either self-dual or not, right? A can be wage below its complement or not, right? If it is, then we get a self-dual class. We get a class that's closed under complements. Otherwise, we get a pair of classes, the class of A and the class of the complement of A, like this. So by Wage's theorem, the classes fall into this sort of almost linearly ordered hierarchy that looks like this. Right? Each level is either a complementary pair or a self-dual object. Okay. By the way, so we could call wage determinacy just determinacy for these games, right? So wage determinacy just says that games that look like this are determined. As far as I know, it's an open question whether that implies AD. Right? It could be, so that's just a question, right? Does wage determinacy just imply the full AD? I don't know if there are any partial results, even if this is, no? Okay, so it may be that wage determinacy is just everything in AD. It's not true at the Borel level. Okay, so not for Borel. What's that? It's not true for... Prove that the implication doesn't hold. But it does hold. Oh, I see. I couldn't quite hear what you're saying, but it's true for... Yeah. I see. Pi 1, 2 by 4. Okay. So, yes, in most cases. All right. Now, Martin proved that... Now, what did Tony Martin proved that AD plus DCR implies that the wage hierarchy is well-founded. Right. The proof, however, the use of AD is what? The use of AD is wage determinacy plus the property of Bayer. All sets of reals have the property of Bayer, right? That's enough to show that there's no descending omega sequence in the wage order, right? But it's not enough to show that every set of non-empty set of wage degrees has a least element, right? So you need DCR to get you from one to the other, right? So as far as I know, it's an open question, right, whether AD by itself, well, it's an open question whether AD by itself implies DCR, as far as I know. It's also an open question whether AD implies that the wage order is well-founded by itself. All right. What's that? Yes. Well, okay, so I think it's going to be the same, right? Because the wage classes filtrate into Lipschitz classes in a way that doesn't depend on DCR. So I don't think it, as far as the well-foundedness, it matters. His question? If I replace, you know, I skipped talking about the Lipschitz order, right? And the question was, well, what if I replaced wage with Lipschitz? Does it make any difference for this question, for anything that's going on here? I don't think so. Okay. No, well, yeah, that's true. Yeah, you're right. Yeah, I mean, you know, I'm trying to circumvent, you know, I don't want to get into every detail. You're right that there is some, I'm cheating a little bit by not defining the Lipschitz order and defining the relationship between the Lipschitz order and the wage order. But I think morally these are still interesting questions and open questions. Yes. Martin's theorem? That's it, right? Literally what did I write? I wrote AD plus DCR implies that the wage order is well-founded. Right, and I said that the use of AD is just wage determinacy plus all sets of reals have the property of Bayer. Right, so that's all you need from AD. What's that? You could use measure, I guess, yeah, right. Yeah, you maybe, yeah. So I guess you could use measure. But you don't have to, yeah. Yeah, that's true. No, I'm happy, yeah. Yeah, that's what I wanted. Okay. All right. Actually, so there's a nice theorem of Steele and Van Wessem that completes the picture at limit stages, and I think it doesn't use DCR. I think it just follows from AD. Right, we have that the wage hierarchy breaks into these classes, which are either dual or self-dual, and they're linearly ordered according to AD, and they're well-ordered. If we throw in DCR in particular, you may ask, well, what happens at limit stages? And so Steele and Van Wessem showed that at limit stages, the next order, I mean, you have to, well, yeah, limit classes, I don't think it just requires DCR. Limit classes are self-dual exactly when they have countable cofinality. So. exactly when they have countable cofinality. Well, let's say it this way. When the wage order below them has countable cofinality. Okay. All right, so we get one picture of the wage hierarchy like that. At the limit stages, well, that first stage above, right, a stage that's not a successor stage, right, could be self-dual or not, and it just depends on whether what's below has countable cofinality or not. Okay, so you can't have either possibility there at the next stage. Okay. Now, it's also true, so again, it's shown by Solvay, possibly known before, that there is no largest wage degree. This is really just a diagonalization argument, right? If I have a set of reals A and I want to build, what's that? What's written right here? Limit classes are self-dual, right? I have a wage class, right? And it's not a successor class, and I want to know, is it a self-dual class or not? Yeah? Yeah. Isn't this the theorem, right? That, what's that? Well, yeah, I'm not talking about the initial. Right. That's right. Exactly when is when just if and only if. That's what that's what isn't that what exactly when means? If and only if. Yeah. Right. Yeah, my handwriting is terrible for sure, right. But the limit classes are self-dual. Okay. Yeah, well, the handwriting doesn't help, I'm sure. If and only if. Right? Okay. All right. There's no largest wage degree. If I have a set of reals A, right, I can just diagonalize against it, right? There's a natural coding of continuous functions by reals, right? So I can put f in some set A prime if and only if the function coded by f applied to f is not in A, and just build a set that's wage above A like that. It's not clear to me that if the wage hierarchy was well-founded below A, it's well-founded below A prime, right? As far as I can tell, you might jump from well-founded to ill-founded just by doing this diagonalization. Non-self-dual classes have a simply definable minimal class above them, right? I said the right thing, yeah? Right, if I have a non-self-dual class, right, so A is non-self-dual, right, so here's omega minus A, right, I can build a least class above that pretty easily, right? I just take the things of the form, 0x, x in A, and 1x, x is not in A, like that. I can build the least class above it. As far as I know, if I have a self-dual class, there's no construction that gives you the least class above it. Is there? All right, what's that? Did he do it? Okay, well, I'm sorry. Okay, so I don't know. Yes, that's true? All right, sorry. But, so what's its relationship to this then? What's that? But does it answer this question? Is this one going to be well-founded if the original one was? You think the diagonalization is also well-founded? Okay. All right, I didn't know this. Okay, so, all right, so good. So wage does imply there's, all right. I did ask around, but all right. This is wage. So presuming it's AD then? All right. Each self-dual class has a successor? Okay. I'll have to look it up. All right. I didn't think it did. Well, it depends what you mean by cofinality. It really doesn't, I'm not assuming that I'm well-founded below there. The question is there a countable cofinal sequence below there or not? Right. Right, but there may not be a next class, right? That's the whole point, right? Right. Yeah. I think the theorem is still true without, I mean, you may be way up in the ill-founded classes and you want to know, are you self-dual or not? So just look at what's below, and is there a cofinal sequence or not? A countable cofinal sequence or not? And that tells you whether you're self-dual or not. No, I'm starting with a class that is, I'm starting with a class and saying just look at what's below it. I'm assuming the class I start with is a limit. Yeah, so I'm not asking DCR to find it. Okay. What's next? Theta. Right. Theta is the least ordinal, which is not a surjection of the reals. Right. This is the definition of theta. It's not a surjective image of the reals, the bare space. Let's not say that. Okay. All right. Let's observe, right, that assuming that A, some set A, has wage rank alpha, there exists a surjection from the reals to alpha, right? Because if I take a code for a continuous function, I can just map it to the wage rank of the preimage, right? So I can just send f to the wage rank of the preimage of f of A under f hat, like that, right? Right. So that maps the reals onto the sets of reals that have wage rank below me. Okay. So again, assuming AD plus DCR now, right? Each set of reals has wage rank below theta. All right, the wage ranks all have to be below theta because they give you surjections explicitly. Solvay showed the other half, so Solvay showed that the height of the wage hierarchy is exactly theta. Okay, so Solvay. Right, so, well, okay, it depends how you want to state it. If we want to say it this way, assuming AD plus DCR, the wage hierarchy has height theta. I mean, it's isomorphic to theta once you collapse the non-self-dual degrees, identify them with their partners. I mean, the real theorem behind this, I think, is just a ZF theorem. It just says, under ZF, for all alpha below theta, there exists a wage increasing sequence of length alpha. Right? The point being, well, you can use this diagonalization trick to get you from successors, right? And you just fix one surjection, one witness to alpha being less than theta, and that lets you do some bookkeeping to glue your sets together as you build, right? So just about anything, there's a wage increasing sequence of length, each alpha below theta, whether or not the wage hierarchy is well-founded, right? You can always shoot a sequence like that. So if it happens to be well-founded, it has height exactly theta. We're more or less at 45 minutes. If you want to take a 5-minute break, we can do that. Or if you want to just, no? You're all having fun. Okay, good. Let me know. All right. Very good. Okay. Suslin sets and infinity Borel sets. And infinity Borel sets. Okay, so again, so for us a tree, right? We know what a tree is. All right, so let's just, it's given a tree T, which is contained in omega cross, well, really, let's just say gamma, so the less than omega, right, for some ordinal gamma. Right, the projection of the tree is the set of X in the bare space for which there exists an F in gamma to the omega, such that for all n, the pair X restricted to n, F restricted to n is in the tree, which is the same thing as saying just the pair XF is a path, is an infinite path through the tree, like this. I hope you can read some of that. Okay, so we say that A is Suslin. Well, we can even say A is gamma Suslin if A is the projection of T for some tree T on, or whatever, contained in omega times gamma to the less than omega, like that. And it's Suslin if it's gamma Suslin for some gamma. Okay. Now, the first thing we should observe is that Suslin sets can be uniformized. Right? So, if A contained in, I guess I didn't, I can certainly add one more coordinate, which I didn't here, right? So, I defined this for subsets of the bare space. It makes perfectly good sense for subsets of the bare space cross itself. If a subset of the bare space is Suslin, then it can be uniformized. There's a uniformizing function. Right, so if A, right, is what? It's the set of xy such that there exists an F, right, such that x, y, F is a path through the tree, right? Then, all right, for each given x, I can find the what we call the leftmost branch. Since gamma is well-founded, there's sort of a canonical least branch that is a branch of this tree, if there is one, okay? So if I have a Suslin set, I can uniformize it. So in particular, right, in L of R, not all sets of reals are going to be Suslin, which I will say in a second, and get my order down here. I guess we can, all right, so I have a sequence of observations, so note a few things about this, right? The Suslin sets, so one, form an initial segment of the wage hierarchy. Right. If I have a Suslin representation for a set, and I have a wage reduction to some smaller set, I can use that continuous function to build me a tree showing that the reduced set is also Suslin. Okay, I said they're uniformized. Good. What else? Yeah, so I also said this, right? So models of the form, as a result of this, of the form L of A and R, where A is contained in the bare space, right, are not going to satisfy that all sets of reals are Suslin, because they don't satisfy uniformization. All right, Martin and Steele characterize exactly what the Suslin sets are in L of R, so assuming AD. All right, so AD plus B equals L of R implies that the Suslin sets are exactly the sigma 2-1 sets, boldface sigma 2-1 sets. Okay. All right. Now for us, one observation, I guess observation 4 about this is that if I have a tree So given a tree T on omega cross gamma, right, for some ordinal gamma, right, for all x in the Baire space, x is in the projection of T if and only if the model L of T and x thinks so. This is just absoluteness of well-foundedness, right? So if I have a tree, right, it projects to some set of reals, right? All you need to do is to figure out whether a given real is in the projection of the tree is to see the tree and the real itself, okay? All right. So the Souslin representation, well, gives you a code for a set. All right. Now, in L of R, in models of the form L of A and R, not every set of reals can be Souslin, but we turn this, or Hugh turned this into the next best thing. So I think I'm ready to give the definition. Okay, so we're going to convert this into a definition. And again, this is Hugh's definition, I think. All right. A set A contained in the Baire space is infinity Borel if and only if there exists a formula phi, right, and a set S contained in the ordinals, right, such that A is the set of X in the Baire space, such that L of S and X thinks the formula phi of S and X, like this. Okay. Now, there's a few things to say about this. Many, many things to say about it. The first thing to say is that Souslin sets are infinity Borel, right? And the trees that project to the sets have exactly this property by what we just said right here. One thing to say is, you know, it's not totally, I mean, okay, these are standard moves that everyone's familiar with. It's you know, I get hung up on things that nobody cares about, but it's not really a legitimate definition as written. You know, you want to say something like, there is an ordinal gamma, right? So maybe I want to say one more thing, right? There's an ordinal gamma such that A is the set of X in omega the omega, such that L gamma of S and X thinks phi of S and X like that. Now it's, you know, now I feel better with this as a real definition. There's only set many reals, and so that's equivalent. The non-definition is equivalent to the real definition. I mean, well, it's equivalent to the second thing, which is a definition. Now, in fact, this isn't the real definition, and I'm not going to tell you the real definition in this lecture. Eventually, we're going to have to say what the real definition of infinity Borel is. I mean, it's not even evident why it's called infinity Borel. This definition doesn't explain the name at all, but when we give the real definition, we will see why it's called infinity Borel. Steve called this pair, I think Steve called the pair phi S an infinity Borel code for A. It's actually going to matter. I'm going to call it an infinity Borel star code. It's, you know, something else is going to be an infinity Borel code. It's going to be equivalent, but, you know, just doing this is the easiest thing to tell you right now, but it's somehow not really the definition we're going to use eventually for what an infinity Borel set is. Okay. Very good. Souslin sets are infinity Borel. What else can I tell you? Infinity Borel sets have infinity Borel codes. I mean, oh, okay, fine. So I'll just, more notes about these things. Right. So I'll start the list again, right? If A has infinity Borel code or infinity Borel star code, then it has one with S a bounded subset of theta. Right, you can just take an elementary submodel. If you have an arbitrary infinity Borel code where S is some big set of reals, you can just collapse it down. Not a set of ordinals. You can collapse it down to one where S is a bounded subset of theta. Right? Everything interesting is going to happen below theta. What is next on the list? Oh, I mean, okay. So here, this is really not really super relevant to the rest of the talk, but just to give you one sort of amusing consequence of being infinity Borel, right? If A is infinity Borel, right, and aleph 1 is not below 2 to the aleph 0, there's no omega 1 sequence of reals, then A has the property of Bayer, is Lebesgue measurable, etc. Right? Why? Well, I can just look in my model L of S, to get property of Bayer. Well, there isn't an omega 1 sequence of reals, so measure 1 many reals are Cohen generic over L of S. Right? So I can force with Cohen forcing, right? And I can ask for the various conditions in Cohen's forcing, are they going to force X, the generic X, to satisfy my formula or not, right? And that's going to be decided by an antichain, and that antichain is just going to give me the representation that shows that set of reals has the property of Bayer, right? And I can do the same thing for random forcing, right? Measure 1 many reals are random over this. I do random forcing, I get a representation that shows the set of reals is Lebesgue measurable on this, right? And so on. Any forcing that exists in L of S, I can do this and get regularity relative to it. Right? Okay. That's in the background. We're not really going to use that, I don't think, for anything. What else do I want to say? Infinity Borel sets are also an initial segment of the wage hierarchy. I think that's also clear from, right? Also form of the wage hierarchy. I guess that's clear, right? I could just throw a code for my continuous function into S, right, and just compute the wage reduction that way. What else? Okay. I think I've told you all the soft things I want to tell you about this. I'm going to write down some target theorems. And so now I'm actually going to write down some things that I hope to, everything is obviously taking much, much longer than I thought it would, which is probably what I should have expected. But, all right, so I'm going to write down some target theorems, which maybe we will prove eventually, if I speed up dramatically or something. Yeah, right. So Suslin implies infinity Borel, right? Okay, but Suslin sets are uniformizable, so, right, not every set of reals in L of R is infinity Borel. Okay, so I'll write down the first target theorem, which sort of completes that thought, I guess, right? Okay, so theorem, and then these are all due to Q, I believe. Right? Oh. I'm going to complete that thought, but then I'm going to go back to some other thought if I remember to do it. So AD plus V equals L of R implies all sets of reals in infinity Borel. Right, so in L of R, if we have AD, the Suslin sets are exactly the sigma 2-1 sets. They stop at some proper initial segment of the wage hierarchy, right? But the rest of the wage hierarchy is all infinity Borel in that case. Everything is infinity Borel in L of R. Yeah, the one thought that I skipped, which I could stick on this list, is the infinity Borel sets are not necessarily the same thing as the smallest. Oh, nope, that's just in the next lecture. Never mind. Never mind. I will say that on Thursday. Okay, so that's sort of target theorem 1. Let me write down some of what the other ones are. And this is proved in the book, but what else do I want to go for? And again, I believe these are all due to Hugh. ADR plus DC, right? AD, not ADR. If AD plus DCR holds, and A is infinity Borel, then it is infinity Borel in L of A and R. Right? So the property of being infinity Borel reflects down to the smallest model that contains the real in A, which is again something that Suslin-ness doesn't do. Right? Suslin-ness doesn't reflect down to the smallest model. Right? You can have sets that are Suslin. I haven't actually quite said that yet, but I will. Right? You can have sets that are Suslin in L of P of R, but not in L of themselves and R. Right? So the infinity Borel property reflects down, but Suslin-ness doesn't. Okay. AD plus uniformization implies that all sets of reals are infinity Borel. Assuming AD plus DCR, for all A contained in the Baire space, A is infinity Borel if and only if there exists an S contained in the ordinals such that A is in L of S and R. Is this the theorem you said in your talk? Maybe it's not. I think it's a different one. Right, it's certainly clear that if A is infinity Borel, then the infinity Borel code, right, A is in L of S and R, where S is the infinity Borel code, right? But the reverse happens as well for infinity Borel sets. And now these are all, okay, so in my possibly too ambitious plan for these talks, I wanted to at least sketch proofs of all of these things. This one is different. These three, no, hold on, which ones are different? These two are different. These two follow from similar machinery, which is sort of the main thing I wanted to get to eventually in the talks. We will see. We'll see how far I'm able to get. Anyway, these are some targets, possibly too ambitious targets. There's one more theorem which I want to mention, which is not really a reasonable target, but it's an extension of that same machinery. Which is the following, is okay, so assuming ZF plus AD plus DC now, the full DC, for all lambda less than theta, all sets in power set of the Baire space intersect L of P of lambda are infinity Borel. Okay, and that one, it's an extension of the same techniques, but sort of beyond what I would dream about trying to do. Okay, the one last thing about this, we're still aiming for the definition of AD+, right? We're still trying to define AD+. This is So one of the axioms of AD+, we're going to get there, is that, so one part of AD+ is just the statement that all A contained in the Baire space are infinity Borel. Okay, so we're going to get there eventually. Okay. How's everyone doing? You guys are okay? You want to take a break or anything? Okay. Well, all right. Yeah, I can't. That's very tricky. I don't know. Yeah, no, I'm okay. I think what I'm going to do. Oh, very good. I'll do that. Got some water right here. Okay. So here's the plan for the next 25 minutes, if I can get there. It would be nice if I could define AD+ by the end of the first lecture, which That's sort of my goal at the moment. I'm going to tell you about the last remaining part of AD+, ordinal determinacy, right? And then we can define AD+ at least before we finish. And then that can be enough for today, I guess. Okay, so let's do that. Very good. Well, that was part of the goal for lecture 1. I mean, I can just keep talking, but yeah. I'm going to I will eventually define the Solovay sequence, but no, I was going to. That was going to be the last thing. That was going to be the last part of the first lecture, but probably won't make it. What's that?
I don't need a break right now. I would like to.
Well, eventually. Eventually it'll end. We have a half-hour coffee break after this lecture, so we could. No, I will not make you go past the next 25 minutes. So, all right. Gamma determinacy. Okay. So given an ordinal gamma. Okay, well, at the very beginning, I defined these games that looked like this, right, where X was a set, and X was a set, and A was a subset of this. So I can use that notation one more time, right? So gamma determinacy is the statement that, what's my game going to be? It's the game G gamma F pre-image of A is determined whenever A is contained in the Baire space and F going from the omega sequences from gamma to the omega sequences to the Baire space is continuous. And just to be clear, what's the topology here? So gamma gets the discrete topology. All right, gamma to the omega gets the product topology. Okay. All right, so gamma determinacy says these games are determined. It's a game where we're playing, just to make it explicit, right? 1 and 2 are playing elements of gamma, right? So this is alpha 0 in gamma and alpha 1 in gamma, etc. Right? In the end, we build something, some x that's in gamma to the omega, but now we apply f to it to find out who won the game, right? We apply f to it, and we push down and ask whether this is in A or not, right? And that's how 1 wins. If this, take away the. Okay. Now, one thing, just one special case of this. Sometimes this is all due to Hugh. Sometimes Hugh uses it in the following setting, but not always. But I think the setting sort of makes it a little bit clearer why you might consider games like this, or what a game like this looks like. So one sort of special case or example or something is we have the forcing where we're just going to collapse gamma down to be countable, right? So in this forcing, conditions look like P going from n to gamma, like that for some n. This forcing just adds a surjection from omega to gamma, right? We have a name in this forcing, named tau, for an element of the Baire space. And the game we're going to play, and it's a slight modification of that game, is we're going to play conditions in the forcing, and each condition has to resolve some of the names. So P0 has to decide what tau of 0 is, right? And P1 has to decide what tau of 1 is, and so on. And by the end, we will have realized the name, and then we can ask, is that realization of the name in A or not, right? Right. And the thing that takes us from conditions in the forcing down to the realization of the name is a function, continuous function of this type, right? So it's just one specific example that sort of a game of the type that we care about. And so in some applications of gamma determinacy, you're explicitly doing this, but not always. Okay? All right. Okay. Now, what can I say? First of all, I guess we should observe that omega determinacy is AD, right? So AD just is omega determinacy, right? If my gamma is omega, then it's the same thing as AD. Less than theta determinacy is going to be the third part of AD+. I mean, Hugh calls it ordinal determinacy. I guess I prefer to call it less than theta determinacy. So less than theta determinacy, right, is the statement that for all gamma less than theta, gamma determinacy holds. Okay, and that's going to be the last part of AD+. I guess at this point I can just tell you what AD+ is. So, I mean, getting a little bit ahead of myself, but so definition, right? So AD+ is the conjunction of, okay, well, the definition of AD+ is slightly controversial, I think. I mean, it's the conjunction of either two or three things, depending on whether you think DCR is one of them or not, right? So DCR, all A contained in the bare space R infinity Borel, and less than theta determinacy. Right? Now, I think usually, right, Hugh says, well, these two guys are AD+, but we only talk about AD+ in the context of DCR, right? But, okay. Some people prefer just to add it. If we're always going to assume it when we talk about AD+, why not just add it as an axiom? So you have to be a little careful, I guess. So AD+ is either, may include DCR or may not, depending on who you ask. But DCR is part of the context for AD+. Okay. Now, having said that, I mean, I'm still talking about less than theta determinacy, and that's probably all I'm going to do for the next, whatever it is, 10 or 15 minutes. Let me just tell you a couple things about less than theta determinacy, and then that'll be enough for today, I guess. I want to tell you it's consistent, right? I want to tell you when it holds. That's going to require a little bit of background. Okay, so I have to define a couple things first. Strong partition cardinals. You talked about them in your talk or no? You didn't? Okay. All right. So, right. Kappa, cardinal kappa, is a strong partition cardinal if what? For all ways of taking the kappa-sized subset, for all ways of dividing the kappa-sized subsets of kappa into two pieces, right? There exists a B, which is a kappa-sized subset of kappa, right? Such that for all C, well, either, let's say it this way, either for all C kappa-sized subsets of B, C is in A, right? Or sorry, this is not the way I want to say it. Yeah. It's a strong partition cardinal if, for any function f, going from the kappa-sized subsets of kappa to gamma, where gamma is less than kappa, right? There exists an A, which is a kappa-sized subset of kappa, such that f restricted to the kappa-sized subsets of A is constant. Okay? Now this is inconsistent with choice. Okay? Yeah, so I started to write the version where gamma was 2, right? As far as I can tell, I mean, in the choice context, when you write things like this and you replace gamma with 2, you usually get something equivalent. It's not obvious that you get something equivalent when you replace gamma with 2, right? So give something equivalent. I don't know. Okay. However, the stronger one is witnessed in L of R. So, following theorem: Kekras, Kleinberg, Moskowakis, and Wooden. So, Kekras, Kleinberg, Moskowakis, and Wooden says that under AD, the strong partition cardinals are cofinal in theta. Right? There are cofinally many. In fact, you can say, the theorem is witnessed by the following cardinals. It's witnessed by the cardinals which are delta 2, 1 of A as computed in the models L of A and R. Right? And so you can take A to be as big as you want, wage-wise, and so you can make this as big as you want below theta. The theorem uses a tremendous amount of Cabal-style point class theory, right? I mean, really, I spent the entire summer of 2015 writing down a proof of this theorem with many, many hints from Steve on how to do it, but it's a long, difficult, deep theorem, so I'm not going to talk about the proof at all. But this theorem does give us less than theta determinacy through the following theorem of Hughes. So, almost done. So theorem, and this is Moskowakis and Wooden. And it says the following. So suppose that, I mean, both of these things are in the book, in the notes, right? So suppose that, so DCR holds, we're going to have 3 ordinals. We're going to have gamma is less than lambda is less than, less than kappa is less than lambda. We're going to assume that lambda is a strong partition cardinal. A is a subset of the Baire space. A and its complement are both kappa Suslin. Have I said everything? F going from the Baire space. F going from gamma to the Baire space is continuous. So all of this, I think I've got it all now. Then the game is determined, right? So then the game of the type from less than theta determinacy is determined. So the game on gamma using the payoff set F preimage alpha is determined. Okay. So let's just write down the punchline from this. I don't think it's possible I just forgot to say it, but maybe I'm just using the Suslinness and the strong partition cardinal. Oh, maybe, but maybe I can just pass to a model of... Everything's less than theta. Everything's less than theta, so I can take one set of reals that's big enough to see. Yeah. Oh, I see. So maybe I'm. No, I understand. Yeah. Okay. I mean, I prefer to say it this way, but it doesn't really matter. I mean, it's sort of cosmetic relative to what we want to do. But yeah. Okay. So the punchline for us now is that assuming AD plus DCR less than, well, I could say it this way. Let me just say it. Oh, this is fine. That's what I want to say. Less than theta determinacy holds for games of this form when A is Suslin and co-Suslin. All right, when A is Suslin and so is its complement. All right, then I have less than theta determinacy for those games, right? All right, and I guess the very last thing I want to say is that we can reflect this down into L of A and R using the Moskowakis coding lemma. So, all right. I mean, I hope I'm not rushing it, but let me just, okay. I'm going to make this one. All right. We're sort of cramming this in at the end, but this is not really the full Moskowakis coding lemma. It's sort of a weak form of the Moskowakis coding lemma. Well, I don't know. Maybe it's equivalent. It's a simplified statement of the Moskowakis coding lemma. Which says what? Assuming AD, if A is contained in the Baire space and gamma is below the theta of the model L of A and R, then power set of gamma is contained in L of A and R, and furthermore there exists a surjection from the Baire space to the power set of gamma in L of A and R. Okay. This is the coding lemma. Right. And again, I mean, I'm getting to the end and saying this a little quickly. I may rehash it. What is it saying, right? It's saying if I have an ordinal less than theta and I have a set of reals such that L of A and R sees that ordinal is less than theta, then in fact the whole power set of that ordinal is in L of A and R. So if I have a strategy in one of these games, right, it's a game on gamma, the strategy is essentially coded by a subset of gamma, right? So if I have a set which is big enough to see that I mean, it's wage large enough to see that gamma is below theta, then L of A and R is going to see the strategy in that game. Okay? All right. So, maybe this will be the last thing I say. I see. Yeah, I mean, I basically just said it, so I'll just say it again. So, assuming AD, if A is contained in the Baire space and gamma is below the theta of the model L of A and R, and the game G gamma of F preimage B is determined, right, for some B contained in the Baire space where B is in L of A and R, like that, then it's also determined. Yeah? Okay. Is determined in L of A and R. I don't know. I feel like I'm finishing in the middle of a thought, but this is probably as good a place as any. So what's that? Do I want to give I mean, not right away, I guess. Yeah, I don't know. I feel like I'm sort of up against the time limit. So I'm going to stop here and I'll pick it up on... Yeah, okay. I mean, right. That's right. Okay. Yeah, so putting this all together, sure. Okay, I'll tell you 2 punchlines then, as long as you're waiting. So, yeah. So 2 consequences of what we've done today. So one is that AD plus holds if AD holds and for every A contained in the bare space, let's just say it this way. I'm not going to say it that way. Let's say, and there exists a model M of AD, good, that's fine, such that, V, we are contained in this model, right? We have the same reals as this model, and all sets of reals in V are Suslin in the bigger model. I think I've said this coherently, sort of improvising slightly. As I understand it, this was the motivation for AD plus in the first place. AD plus is what reflects down to us. Our sets of reals may not all be Suslin, but there may be some larger universe out there that has the same reals as us, that sees that all of our sets of reals are Suslin. What information gets passed down to us from that situation? And that's AD plus, right? As I understand it, the original name of AD plus was within scales, the idea being that AD plus is what falls down from Suslin representations that we don't see down to the sets of reals that we do see. Okay. Second consequence of what we've all done is that AD plus, I mean, if you buy this as the meaning of AD plus, the second part also sort of follows morally, but the second one says that if the reals are contained in M, which is contained in V, which satisfies AD plus, then the inner model, the smaller model M, also satisfies AD plus. Because everything we've done reflects down to that smaller model. Okay, but all right, I may say it again more thoroughly next time. Yeah, that is the punchline of what we've been doing. Well, okay, so for example, L of R, right? M could be L of R, right? E.g. Okay, I can say that too, sure. I mean, yes, there are lots of things I want to say. I just want to say them next time. Yeah, right. Right. Yes, it's also true that L of R satisfies that AD implies AD plus, right? And of course, the big question is whether that holds always. Right? So, I mean, this is the sort of, I really did want to say this next time, but the big question is whether AD implies AD plus, right? This is open, right? Right? But it does hold in L of R. Right? If L of R satisfies AD, then it satisfies AD plus. And this is something we've more or less, we've said all the parts of this. I mean, I'll say it more clearly and thoroughly maybe next time, but we've done it. We've outlined it in what we did today. So I will stop. Thank you.